Hello, everyone. Yeah, we have 40 minutes, less one, I guess, less two. 96 slides, and we want to take questions. Let's see how we make it. So I'm gonna talk about infrastructure-related news that some of those described in a keynote, Jensen keynote. In some of others, I'm gonna go deep dive a little bit more. And I'll try to cover everything, or almost everything. So as you know, AI, it's a multi-layer infrastructure. The 5 layers cake started with energy. Need to secure energy in order to build an AI factory. Chips and infrastructure, and then models that runs on top, and then you have the applications. Today I'm gonna try to cover the 3 first one, the vanilla flavor, the chocolate flavor, and strawberry flavor, energy, chips, and infrastructure. And I'm gonna focus more on these areas. Another thing that is happening, and actually drive a lot of innovations and development and co-design between the hardware items, hardware elements, and the software that runs on top of the frameworks and the workloads. Scaling laws, as we moved from pre-training to post-training, to long thinking, and then now to AI talking to AI, there is greater demands on the infrastructure, greater demands on the connectivity that connects GPUs and LPUs and CPUs together in order to build an AI factory. Demands are growing in bandwidth, in latency, in jitter, in reduction operations, in saving energy, and so forth. And this is where we spend a lot of focus, how to develop and build an infrastructure that is co-designed with the application running on top. So you can maximize every watt, every power that you have in the data center, and ability to maximize the performance and the utilization of the compute elements. Now, when we look on the AI factory, there are actually multiple connectivities, multiple infrastructures that needs to come together in order to create an AI factory. First, we start with a scale-up fabric, scale-up connectivity. The scale-up mission is to connect GPU ASICs together and to form a single GPU. A GPU that actually works as one unit. And in order to do that, we need to make sure that all those GPU ASICs are fully synchronized with one another. They're able to send and receive massive amount of bandwidth, be able to support in-network computing operations so we can offload some of the compute into the network and be able to free some of the elements or some of the cycles from the GPU. We need to make sure extremely low latency, but maybe even more important, zero jitter. Every GPU ASIC needs to be completely synchronized with another GPU ASIC in order to make it one unit. And after we build a rack scale GPU, then we need to scale it out because we need to connect hundreds of thousands of GPUs to run a single workload. For that purpose, we have built a scale-out network. And scale-out network has similar characteristics to a scale-up network. The differences are, for example, in the amount of bandwidth that they do support. On the other side, scale-out needs to run distances, which is much larger, much longer than scale-up. It still needs to have highly effective bandwidth, and it still needs to have zero jitter, because you want that rack-scale GPUs to operate synchronously with other rack-scale GPUs. Every time a single GPU is late to receive information compared to any other GPU, the entire system is going to hold. The entire system is going to hold. 100,000 GPUs. One GPU is late, all the rest are waiting. And this is where you lose money. So you need to make sure zero jitter, both scale up and scale out. And after we're scaling out, we need to scale across. Because power, for example, or available power limit how many GPUs or LPUs or CPUs we can put in one place. And sometimes we need larger systems, larger infrastructure, larger AI factories. And in order to build something larger, we need to be able to connect remote AI factories together and make them behave like one for a given workload. So we need to connect over longer distances, but here, while latency will be determined by the distance, we don't want to pay extra latency on top of that. And therefore, we need to actually create or have innovations also on the scale across infrastructure. Recently, we announced a new infrastructure for storage. And we're building new infrastructure for storage, for context storage, to support the growing demand of inferencing. And that's the fourth one. So we have scale up, scale out, we have context memory storage infrastructure, and we have scale across. 4 networks building an AI factory. And as we know, the data center is the computer, or actually the AI factory is the computer, and the element that actually define what that AI factory can do is the network. So that's why the network is critical. Network is the key. Now, when we're focusing on scale out, and we're looking on options that exist, the different options of technologies, there are many kinds of Ethernet. Many kinds of Ethernet. The off-the-shelf Ethernet technologies or product that exist were built for hyperscale clouds or enterprise clouds or long distance. They were built to support single server workloads, which means I need to get the data in the server, I need to get the data out of the server. I don't need really to get the data between servers. And as such, jitter was not important. Jitter was okay. But when we deal with distributed computing workloads, training, inferencing, jitter is the most problematic item. If you have jitter, you create delays. If you create delays, you have GPUs that are just sitting and doing nothing. And for that reason, we had to purposely design network that can fit distributed computing workloads. And that's what we did with Spectrum-X. Purpose-built for AI and co-designed with other elements of the data center. So Spectrum-X, it's not a single device. You cannot build an infrastructure to connect between compute engines at highly effective bandwidth, low latency, and zero jitter, and try to do everything on a single device. Not possible. In order to do something like that, you need to build an infrastructure. It's an end-to-end infrastructure design. And then you break down the elements that are needed and implement them either in the switch, either in the SuperNIC, or other devices. And that's what we did with Spectrum-X Ethernet. So we did several things. First is that we leveraged the end-to-end capabilities of the NIC and the switch, the SuperNIC and the switch. The switch mission is to distribute traffic, unconditionally distribution of traffic. Unlike off-the-shelf Ethernet, we don't put any limitations on the switch when it needs to distribute traffic. We want the switch to find the best available port for every packet. And it's going to be based on its own situation, because the switch may have ports that are more busy, less busy. But it also depends on the conditions of the switches around them. Because if the switch around me or next to me has a failing port, I don't want to send the same amount of traffic to that switch, because I'm just going to create a hotspot. I want to send data to a switch when I know how much that switch can distribute. and not more than that. So when a switch does a distribution, it's based on its own condition, but it's also based on the other switch's conditions. It gets information from other switches in order to do global load balancing, not just local load balancing. Now, the switch doesn't care about data ordering at all. It's not important. It's not the switch problem. The switch problem is just to distribute. Find the best path, send a packet. Find another best path, send the packet there. Just do that. Now, the SuperNIC will take care of data ordering. Okay, data will get to the SuperNIC out of order, and then the SuperNIC will put it back in place directly in the GPU memory. No buffer copies, no extra overhead. You know exactly where to put each packet. That's the SuperNIC mission. Now, the SuperNIC mission on the other side is to control injection rate. Because as the switch does global load balancing, which means a switch will not send more traffic to a switch that may have a link that is down, the SuperNIC will not send traffic to the network when you know that congestion can happen because of that. So the NIC receives telemetry from every place in the network. And based on the telemetry, it knows where there is hotspot, where is no hotspot, where is more traffic, where is less traffic. And based on that, it's going to create or control injection rates. So that combination together forms Spectrum-X. Now, Spectrum-X today has a large ecosystem adoption, which we're very happy. We're very happy to work with our ecosystem partners and customers and have them be able to customize Spectrum-X for them. So we have Spectrum-X switches with FBOSS. We have Spectrum-X switches with Sonic, with Cumulus, with Nexus OS working with Cisco. A full variety of options on the network operating system. So it's adopted in many places, and it's customized, so it's flexible to support different kind of operating systems on top of Spectrum-X infrastructure. Now, these results I showed last time. Let's actually show the advantages of Spectrum-X Ethernet. Running training, comparing Spectrum-X Ethernet to off-the-shelf Ethernet, and we're seeing two things. One, it's much better performance. The second one is consistent performance. No jitter. Because when I have jitter or I have inconsistent performance, I'm stalling the entire AI factory. Everything needs to be consistent. Now, the nice part in Spectrum-X is that it's part of the co-design efforts of NVIDIA. And I'm probably going to say co-design multiple times in this session, so please forgive me on it. If someone is counting and let me know how many I did, I'll give away a T-shirt. No, I'm kidding. I don't have one. But since it's designing, there is a heavy co-design in Spectrum-X that connects to the way that the frameworks runs on top of the GPUs. We can continue and optimize it. We can continue to optimize its networking algorithms based on the modifications of the workloads. And the workloads are changed. There is more overhead that come from the workloads. There is more requirements from the infrastructure, and we need to be able to customize the way that the infrastructure works. So this is an example. This is a recent example. So people that already have Spectrum-X in their factory, now with the next release of software, they can actually get bigger boost of performance, higher boost of performance. Those are 5 nickel operations that represents around 85% of the time spent on the network. 85%. And we're boosting those operations from 2x all the way to 14x. Same Spectrum-X infrastructure. Just got another boost. Now, for scale across, we need to make sure that we are able to effectively connect remote data centers, remote AI factories, which could be 2 kilometers apart, could be 10 kilometers apart, or could be 100 kilometers apart. Today, off-the-shelf Ethernet gives an option to do long-haul distances between data centers. But it's based on debuffers. So the switches that are being used today for long distance have debuffers, which means that the data could be held in the buffer in case of congestion. And the reason there are debuffers in these switches is because you don't know what's going to happen. It's a long distance. It could take half a millisecond. And since I don't know what's going to happen, I need to have a big buffer in the switch so I can hold data because I really don't want to drop it. If I'm dropping data because of congestion, which is what typically off-the-shelf Ethernet does inside a data center, I will need to do a really long time retransmission. So debuffer is a solution that exists on off-the-shelf Ethernet, but it's really not good for AI. And the reason that it's not really good for AI is that when we connect remote AI factories, we know that there is latency between them. There is distance. Every meter, it's 5 nanoseconds. There is distance. But I really don't want to pay 2x or 3x. I just want to pay the distance. And I can work out the distance. I'm going to put the data out of the GPU memory or HBM and put it in the CPU memory and hold it there. And once I'm getting a response, I'm going to put it back. There is ways to hide latencies. But I don't want to hide 3x the latency. And when you have debuffers, it means that those buffers are going to fill. And then you need to drain them. And draining debuffer switches can be 2x and 3x the latency cost. Does not make sense. So we built Scale Across. And Scale Across is based on changing congestion control algorithm and changing load balancing algorithms to actually fit the distance. There is difference in the way that you control the injection rate, if it's a short distance and long distance. If it's short distance, I can be much more aggressive. If it's long distance, I need to be much less aggressive. So by modifying the way that you control injection rate, you can actually build really good infrastructure on long distances. And that's what we did with Scale Across. And with that, we're able to see almost 2x higher nickel performance on long distance. This is 10-kilometer distance. Now, the reason for that is once you use debuffers, data is being held in a switch. And then it takes time to release it. Which means, effectively, on off-the-shelf Ethernet, I'm getting half the bandwidth. And with Spectrum X on Scale Across, I can actually get almost 100% of the bandwidth. That's the reason for the 2x. So we built a great infrastructure for scale-out, Spectrum X Ethernet, used in many places, customized. The network operating system is customized. We're working with multiple partners of us that built their switch systems with Spectrum X silicon inside, different kind of operating systems and so forth. Now the next thing is to look into energy. Because energy defines how many GPUs we can put. How many GPUs we can put in the data center. So we need to save as much power as we can. Now, in a traditional data center, most of the connectivity was copper. And copper is great. Very reliable, very low latency, zero power. But on a scale-out infrastructure, you cannot do copper because it's long distances. So it's optics. And in optics, when you look on the traditional data centers, actually there is a variety of optics. There is different kind of transceivers. You can choose different kind of transceiver if this is DR or FR or single mode or multi-mode or ZR. There is different kind of transceiver for different missions and so forth. And then you can change and decide which one you want and so forth. But if your mission is not really flexibility, but you want to minimize power, this is where optical goes into co-design. This is where you need to co-design optics. Now, of course, there is different attempts on pluggable transceivers trying to reduce power. They go from full read time to half read time to LPO, for example, trying to reduce power. Is those elements or LPO give me the best power or the least amount of power that I need to invest? The answer is no. It at least 2x more than if I would go co-design and package the optical engines together with the networking pieces. At least half. You get at least half, or it's like more than 2x. That's one thing. The second thing is that while minimizing power, I do want to try and increase resiliency of the data center. And increasing resiliency, one way to do that is to reduce the number of components. And when we're building hundreds of thousands of GPUs in AI factories and going to a million GPU in AI factory, number of components is huge. If I'm using pluggable transceivers on scale out, for every GPU, I have 6 transceivers. And every transceiver, I may have DSP, I may not have DSP, but I have 8 lasers. That's a huge amount of components. So if I can reduce power and increase resiliency by reducing components, that's actually a good thing. So this is where we co-designing optics. And co-designing optics means co-package optics. So we are co-packaging the optical engine together with the switch device. One package. We innovated with TSMC to create the right packaging so we can actually do a full validation of it, because it needs to be robust, it needs to be reliable. We needed to work with partners to create the right laser sources, to ability to reduce the number of lasers by 4x. We work with partners in order to build the right fiber arrays, because we wanted to do full alignment on the optical engine. We want to build something that can go to mass production and be robust and reliable, increase resiliency of the data center, and reduce power and consumptions. And we build switches. So this is, for example, the InfiniBand switch, and you can see the different components. There is a silicon photonic ASIC, and there is electronic ASIC, because essentially you are moving electricity to light to electricity, and you want to do that in the least amount of distance before it goes to the switch. That's why we co-packaging it. And then we have the COOP packaging to bring that all together, and then the way that you put the fiber arrays and so forth. There is a huge amount of technology being built here. And we build it with a large ecosystem of us, and we continue to invest in order to build all the things that we need. And this is the first co-package optics for 200 gig SerDes. The first one. And by reducing the power, just think about it, on the same ISO power of the network, we can connect 3x more GPUs. That's a big effect. Now, it's not just that. We're actually increasing AI uptime. Co-package optics means that the optical engines is packaged together with the switch. Closed package. It's robust. There is no human touch. Liquid cooled on top of that. We're getting 5x higher AI uptime, moving from pluggables to co-package optics on scale out. So we did that, right? So we designed Spectrum X Ethernet, purposely built for AI. We did co-design optics, reduce power, increasing resiliency. Now we need to innovate on storage, because the storage requirements are growing. If we look on inference context, the data sits in the GPU memory, in the HBM, or in the host memory, or in the SSD inside of the GPU server. But if it does not fit there, it needs to go to the network storage. That's how we built AI factories so far. Goes to the traditional storage. Now, as context memory increases, KV cache sizes increases, it does not fit the GPU server anymore, which means that we need to scale network storage. But scaling network storage is expensive. Expensive in power. Now, the nice part in inference context is that if you lose a little bit data, you can actually recalculate it. The reason that we invested, that network storage consume power and cost is because network storage mission is to protect the data in the storage. Duplicated data, make sure the data is not lost in the storage. But for inference context, if in the rare case that something happened, I can just recalculate it. So why do I need to invest so much? And essentially what we created, it's a new class of storage based on Bluefield. Bluefield for STX, a new class of storage. We have placed storage racks inside of the Vera Rubin pod, connect directly to Vera Rubin nodes. And we run the entire storage stack of context on Bluefield. So one device. Completely co-designed with the GPU, completely co-designed with the storage that exists in a storage box. And you create something that increases token throughput by 5x. And increase power efficiency by 5x. It's kind of easy number to remember. That's the innovation around storage. Co-design storage. Now, it's not just come by itself because we're building infrastructures, not devices. So we have the GPU with Bluefield, connects to Spectrum-X Ethernet, connects to Bluefield for storage, STX. And the same elements of scale-out Spectrum-X Ethernet, from ensuring highest effective bandwidth, we're using the same thing for storage. Because if you're going to use off-the-shelf Ethernet for storage, we're going to get like 50-60% efficiency on it. I want to get 100% efficiency. So based on the size of the files, you can see there from 5 gigabyte files all the way to 50 gigabyte files. We're getting close to 1.5x performance increase when using Spectrum-X Ethernet for the storage access versus off-the-shelf Ethernet. You know, Spectrum-X Ethernet, it's like a present that never stops giving. And it's just getting better and better. Co-design, you know, we're improving the software that runs on top of that, and we're actually getting boost in performance. So there is an infrastructure for storage, a new infrastructure for storage. Bluefield 4 storage processor, combining Vera and CX9s, combining the technology of Vera and CX9s, 2 CX9s actually. Each Bluefield 4 Vera enables 1.6 tera of network bandwidth out of it. Docker that runs on top of that. That's the software framework that runs on top of that. That actually brings the entire storage offload, the entire storage accelerations, and then you have the storage stack that sits on top of that. Spectrum-X Ethernet for the connectivity, and then Dynamo, which orchestrates the inference KV cache across all the tiers. Across the pod, and across the pod itself, and across multiple pods. So now we re-architected storage. We co-designed storage. And the next thing is we wanted to bring everything together. So we created reference architecture for the pods. But people they don't build just pods. They're building entire area factories. So you need to make sure that you have the energy and the cooling and the way that you build everything and so forth. So if you watch the keynote, I think it was a great demonstration of and simulations on AI Factory, the reference architecture of AI Factory, with so many partners that participate in order to create that reference architecture. So everything exists inside, and we have libraries, and then there is best practices on top of that. But I want to focus on DSX Sim, the simulator of the infrastructure. And when we look on infrastructure, this is a small setup. Okay, this is a view of the network actually, but a small setup. Just think about how many connections you have. And this actually shows the complexity of Spectrum X. But when you go and build something like that, you need to make sure that everything works. Everything is configured correctly. Now, typically, how do I build a data center? It's like I'm buying the devices, I'm buying the components, I'm buying the servers, buying the switches, connecting them together, and then I need to go and configure all the switches, and that takes time. And there's bugs. So it takes time to configure and get data center from the time that I build it till actually it operates. Now, what happens when I have a software upgrade? Holy crap. Then I need to do a software upgrade, and then I need to make sure that everything works, and if it doesn't, I need to debug that, so that's take time. And when you build $1 billion data centers or factories, you don't have that money to spend more, okay? You don't have the money to have the GPUs, sitting idle. It's like you want them to work all the time. So this is why we created DSX Air. It's a full simulator of the data center. It simulates the network, it simulates the compute engines, it simulates the GPU, it simulates the storage. And we have multiple partners that actually provided their instance. So storage partner of us gave us the storage instance, which we connect to the simulator. And it's actually simulate exactly how the storage works. We have the elements that actually represent GPUs and exactly how the GPU work. And then the switches and the SuperNICs and the DPUs. It simulates the entire data center. And you can configure the data center in that simulator and let it run. And once you have it run, you can copy the full configs in one click to all of the switches in the infrastructure. And that's ensured that's going to work first time. So we did make an announcement, and I think in the announcement we may call some partner of us that actually provide some of their experience. But I can tell you that for infrastructure validation, so from the time you start putting things in the data center until you make sure everything works, and you can go to production, it can take months. With DSX Air, we took 6 months to 1 week. Those are customers' testimonials, not mine. For software bring up, you have a new software, you want to bring it up, you want to test it. 3 months to 1 week. And then development time, 2 weeks to 1 day. That's the power of DSX Air. Now, DSX Air run its operations. I do encourage you to use it with DSX, by the way, or if you have your own data centers, you actually can build that digital twin in DSX Air and run it there. I got 5 minutes and like 60 slides. Oh, boy. Okay. One last thing. Topologies. Topologies are important. Topologies is maybe the one thing that people don't really understand the importance of them. So we brought an innovation in topologies in the way you connect the SuperNICs and the switches a few years ago when we created multi-rail. Because in a traditional data center design like this one, all the GPUs connect to a single switch. But GPUs are connected on NVLink. So the GPUs that sit on NVLink, on the same OS instance of NVLink, already communicated between themselves. The last thing they want to do is to do another communications in a top-of-rack switch. Actually, GPU number 1 wants to talk with another GPU number 1 on another node, not with its neighbor. So this topology is really bad for AI. This topology will create congestion for AI. And from that reason, we created multi-rail. And we came out and says, hey guys, needs to go multi-rail. Multi-rail is that every GPU on the same NVLink OS instance needs to go to a different switch. So the switch topology is based on the way the GPU communicate in reality. That reduces congestion. And when you go 4 rails, if I did the 1 rail before, I had 2K GPUs on the same radix of a switch. If I'm going to 4 rails, I can do 8K. Same size of the infrastructure, same number of layers. And I'm keeping that to 2 layers only. This is, by the way, how 2K looks like. It's like, I try to count when it's hard. And then essentially we're talking about 8K, so it's like 4 of those. That's what you simulate with DSX Air, by the way. Now we're introducing another click. Multiplane. Multiplane. So, for example, when you have a SuperNIC with 800 gig port, that 800 gig port is actually built with 4 ports of 200, 4 lanes of 200 that works as 1 unit. But if I can spread those 4 into 4 separate ports of 200 gig, they can do something unique. Now, you can say, well, wait. Multi-port NIC, that's not something new. That's old. I can use multi-port NIC today. And that's correct. But when you use a multi-port NIC today, the load balancing on those 4 ports is done in software, which means it's not effective. What we did here is the same thing we did in the switch, in our SuperNIC. Load balancing on those 4 ports is done in hardware, based on all the rules that the switch does. Congestion control, every packet can go to a different place. The same IP of Spectrum-X now runs in Spectrum-X in the SuperNIC in full hardware. So now what we can do, we can actually go and start load balancing and congestion control that is start at the switch level, now at the SuperNIC level. So we can use more ports, not just the big pipes, we can use more pipes. So for example, this is just showing you 4 planes, but we can do 8 planes. I know I'm going to steal a minute. Sorry for that. Yeah. We can do 8 planes. This is just doing 4 planes because if I would did 8, that's you will not be able to see it. Okay, so this is 4 lanes of 200 gig. Actually, with Vera Rubin, we have 1.6 tera coming out from the GPU through the SuperNIC. So we have 8 lanes of 200. Okay, just think about it. Not as 4 as 8. So now, with 8 planes, I can do 128,000 GPUs, 2-level factory. Just 2 layers. And if I'm going to combine multi-plane and multi-rail, well, by the way, this is like how 16K looks like. We're talking about 128K. If I do 8 planes, 4 rails, 500,000 GPUs, 2-level network. Now, it's not just that network, it's much more resilient. Because if you lose a switch, you just lose 6% of bandwidth to the GPU. Only 6%, not 100%. And then we also have an AI Ops. AI Ops is the last thing I'm going to show you. It's actually a framework that collects all the telemetry that exists from everything that exists in the data center and do deep analysis using AI to figure out exactly what's the issue. So this is a run, by the way, of there is 10 AI factories here. There is 10 AI factories, and we have an issue in performance in one of them. And actually, we have an AI Ops that goes and takes the entire telemetry information and actually be able to pinpoint exactly what's the issue. In that case, it was 1 link bit error rate that needs to be replaced. But that's ability to quickly analyze the entire telemetry information that exists, and with AI Ops, actually pinpoint exactly what the issue is. And with that, no time for questions. Sorry about that. Sorry, but I'm going to end with the roadmap. So, we're Rubin. We talked about Feynman. And Feynman, we can continue to invest in optics, co-design optics, co-designing optics, and we'll bring CPO to NVLink too. So, when we build NVLink domains, if the domains is small within the rack, we'll use copper. Every place we can use copper, we'll use copper. Nothing best than copper. But when we build larger domain, there is 1152 co-packaged optics. That's why we're investing in optics. And with that, I want to thank you very much. Sorry, no time for questions because she's going to kill me. Trying to stay alive. Thank you very much.